Now we're going to talk quickly about estimating effect sizes in regression-based methods, and then we'll talk a little bit more about what we can do with them afterwards. So R squared is an effect size for a full regression model. It's a really common effect size and can be very informative and useful. So it represents the proportion of total variance in the outcome variable accounted for by the predictors. So we're computing this by dividing the sums of squared residuals from the model by the total sums of squared errors between each observation and the outcome variable and the mean of the outcome variable. So it's essentially the sums of squares in the error of the model that we fit, and then the sums of squares total for our response variable. And so this represents the unaccounted proportion of variance. And then we can subtract that from 1, and that gives us the accounted proportion. So in standard notation, we can write R squares like this. So it's the sum of all squared residuals in the numerator, and then in the denominator, it's the sum, actually that should be squared. I will correct that. This denominator should be yj minus y bar squared. So it's the sum of all of each observation subtracted from the outcome variable's mean squared. And so that's how we can get R squared using standard notation. In matrix notation, we compute R squared by taking 1 minus the vector of residuals transposed by itself. And then in the denominator, we have the vector of y's minus the mean of y times L transposed times itself again. Where L is, just like we've seen in the past, it's just a vector of ones. So that essentially it's just expanding the mean out. So you have a vector of length n that is just the mean repeated over and over again. So using the first example that we saw in the previous slides, where we had 5 observations, we can get epsilon as the difference, or the vector of residuals as the difference between our actual observed response variable and the response variable as estimated by the model. So here, to get the response as estimated by the model, I'm just taking the intercept that I estimated in beta hat, and then the coefficient, and multiplying it by x. So that gives me my estimated y's, which I'm calling y hat. Then I take y minus y hat, and that gives me my residuals, which I'm calling epsilon here. So then I can get my L vector, and then my mean of y, and then I just plug everything in essentially. So for the numerator, I'm taking epsilon transpose times epsilon. And for the denominator, I'm taking y minus y bar times L transpose times itself. So I get 6 and 46. This is the sums of squares from the error in my model, and this is the total sums of squared error for my y variable. And that gives us our R squared. 1 minus that ratio gives us our R squared. So like we've seen with Eta-squared before, R squared is a little bit biased, especially in small sample sizes. Another way to think of this is that it's overfit to the data. So it's going to be a little bit overly sensitive to any noise in the data. So adjusted R squared gives us a little bit of a penalty that will tend to be a better estimate of the population effect in smaller samples. And so we adjust, we adjust based on the sample size as shown here. Where again, P is the number of predictors as well. And so here, n equals 5, P equals 1, so I can just plug everything in. And that gives me my adjusted R squared. So both of these are included in the summary output for an LM object in R. But if you want to just save a step and get the R squared, you can use the R2 function from the performance package. And so you can see there's our R squared and adjusted R squared, which match the results that we got here, 0.87, and here, 0.826. So R squared is actually identical to Eta squared in a sense. In regression-based ANOVA, we can show that the sums of squared for the residuals from the model is actually the same as the sums of squares within. So epsilon transpose epsilon equals SSW, and the total sums of squares is equivalent to the denominator, this y minus y bar L transpose itself. That's the same as sum of squares total. So therefore 1 minus SS within, which is the same thing that we have here, divided by SS total, which is the same thing we have here. So this is the same as our R squared ratio, is equivalent to SSB divided by SST, because SSB plus SSW is SST. And that's the definition of eta squared, and also the definition of R squared. And so we can see this in an ANOVA example. So here I'm just doing the same R squared computation I just did. It's just in the ANOVA type model, where I have the grouping variables. And so here you note that I have the intercept from my ANOVA plus the first coefficient times group 2, and then the second coefficient times group 3. We leave out group 1 because that is the reference group. And so I just then do all the same steps and I get my R square. And so that's identical to what we get if we just check eta square. So here I'm getting eta squared from the effect size package. It's rounded off, but it's 0.89, so it's the same. So adjusted R squared, for adjusted R squared, how many predictors do we have in our one-way ANOVA? So if there were 3 groups, that means that P equals 2, because one group gets dropped as the reference group. That doesn't have a beta predictor associated with it. So we can get our adjusted R squared here, and again, it matches up to our R squared result from the R2 function. But while R squared and R squared and eta squared are identical, adjusted R squared and omega squared are not identical. Remember, omega squared is conceptually similar to adjusted R squared. It's a penalized version of eta squared, but it has a different penalty. And so you can go back to some of the old slides and see what the penalty for omega squared was. And we can see it's actually a little bit different than the adjusted R squared here. Our adjusted R squared here is slightly higher. So they're similar conceptual effect sizes, but they're doing something slightly different. And so we will talk a little bit more about what we can do with these effect sizes in the next slides, and then also get to multivariate multiple regression.